Hi, so for today we are going to continue our discussion about 1001 solved integral. So we are now at number 86. So we'll be solving from number 86 to 90 for today. So we have this type of integral. We have the integral of cosine raised to 4x minus sine raised to 4x dx. So first, if we are going to notice, this is actually a product of the difference. So we can rewrite this cosine 4x minus sine 4x. If you may wish to recall, if you have a squared minus b squared, we can factor it out as a minus b and a plus b. But since this is already in the terms of raised to 4, so we'll be having a squared minus b squared and then a squared plus b squared. So the same principle, same concept that we are going to use. So we have cosine raised to cosine squared x minus sine squared x, and then we have cosine squared x plus sine squared x. Okay, so that we have performed, or we have at least somehow simplified. So as you can see, using the trigonometric identity, Pythagorean identity, that cosine squared x plus sine squared x equals 1 by Pythagorean identity. So it's already discarded. So our integral would look like this. So we have cosine squared x minus sine squared x, and then we have the dx in here. Okay, so that is our basic uh, um, what they call it, simplification. And of course, we also have identity for the cosine squared x minus sine squared x. I think it's the double angle identity, and that is technically equal to cosine of 2x. So yeah, now our integral reduces to simply the cosine of 2x dx, of which this cosine 2x of 2x dx is readily integrable. So if we let u equals 2x, then we have du equals 2 dx. I only have dx here, so I would isolate dx on the right side so that I can perform the u substitution. So now, our integral reduces to cosine of u, and of course, the dx should be multiplied or should be substituted by du all over 2. So that we have 1 half. We can factor out the 1 half because it's constant. So we have cosine of u du. And cosine of u du is readily integrable. So we have 1 half sine of u plus c. But take note, we have to go back to the original variable. So but u equals, we have 2x. So we have 1 half sine of 2x plus c. So this would be our final answer for number 86. Okay, next one. For number 87, we're going to solve some integral again. So 87, we have the integral of the cosine of x plus 2 sine of x squared all over we have cosine of x dx. Now, we don't have any choice. In this given integral, we are going to first expand the numerator. So using FOIL, of course. So the first term, you square the first term. That's the technique. So that's cosine squared x. So the second term would be cosine x times 2 sine of x. That is 2 sine x cosine x multiplied by 2. So that would be plus 4 sine x cosine x. And the last term for our expansion in this binomial expansion. So we're going to square the last term. Okay, upon squaring that, that would be 4 sine squared of x. So we have already expanded the numerator. And this is cosine of x. Let me just rearrange the, or have a nice uh, drawing of line there. So yeah, here is our given integral. But notice if I'm going to rewrite, okay, if I'm going to rewrite uh, the numerator as this, 4 sine squared of x, then plus cosine squared of x, plus 4 sine of x cosine of x dx all over cosine of x. Now, I can actually substitute the value of 4 sine squared of x here. So, what I do, 4 sine squared of x plus cosine squared of x. Okay, I will reduce this 4 sine squared of x cosine squared. Remember that from our Pythagorean theorem, we have sine squared of x plus cosine squared of x equals 1. So I have here sine squared of x. So I have cosine squared of x equals, I'm going to isolate sine squared of x, sorry. So we have sine squared of x, then 1 minus cosine squared of x. So if I'm going to substitute that, so we have 4, 1 minus cosine squared of x plus cosine squared of x. Okay, this term. Distributing, we have 4 minus 4 cosine squared of x plus cosine squared of x. So negative 4 cosine squared of x plus cosine squared of x, we can simplify that. So that becomes 4, negative 4 plus 1 is negative 3 cosine squared of x. So now I have reduced this given term as simply 4 minus 3 cosine squared of x. So we have now what? We have now 4 minus 3 cosine squared of x plus 4 sine of x cosine of x. Okay? All over cosine of x. And by simply using the properties of integral, the sum and difference, we can rewrite the given integral as this. So we have 4 dx all over cosine of x minus 3 cosine squared of x all over cosine of x dx plus we have 4 sine of x cosine of x all over cosine of x. Okay? So now we can cancel this. We can also cancel this so that our integrals are now ready to integrate, readily integrable. So we can factor out 4. We have dx all over cosine of x minus we have 3 outside of the integral sign. Then we have cosine of x dx plus we have 4 integral of sine of x dx. Now, using the all of these terms, except for the first term, are readily integrable. Except for this, no? So, this is readily integrable, this is readily integrable. But if you are going to recall, 1 all over cosine of x equals secant of x by Pythagorean identities. Reciprocal. So, we have 4 integral of secant of x dx minus 3 integral of cosine of x dx plus 4 integral of sine of x dx. So, these are all readily integrable. We have the integral of secant of x as ln. So, you have 4, the ln of secant of x plus tangent of x. Okay, so that's the integral. The integral of cosine is sine, 3 sine of x. The integral of sine is negative cosine. So, this becomes negative 4 cosine of x because of the integral of sine, which is negative. So, that this is negative. Negative 4x plus c. So this will be our answer for this second problem. Number 86, if I'm not mistaken. 87. Okay. So yeah, for number 88, we have the integral of 1 minus cosine 2y all over 1 plus cosine 2y dy. Okay. So again, here, we have seen cosine 2y. We're going to use the identity, the double angle identity. So cosine 2y would be cosine squared y minus sine squared y. So that's the identity that we're going to use. So basically, this becomes 1 minus the cosine squared 2y. So that become cosine 2y is now equal to cosine squared y. So cosine squared y minus sine squared y dy all over, we have 1 plus cosine squared y minus sine squared y d. Okay, no dy already. I have already written the dy. So that is the simplified form if we are going to use the integral. Now, distributing the uh, the signs, no? So if we're going to distribute that, so that would become 1 minus cosine squared y plus sine squared y. Okay? And over, we have 1 plus cosine squared y minus sine squared y, and then dy. Now, notice also that we can actually, what? We can again, okay, transform this and also the denominator, the 1 minus sine squared y. So, let's see, no? If I'm going to rewrite it again, that would be 1 minus cosine squared y plus sine squared y. And on the denominator, I have 1 minus sine squared y, and then we have plus cosine squared y dy. So, both of this, we can use the Pythagorean identity that we have sine squared y plus cosine squared y equals 1. So since we have 1 minus cosine squared y, sine squared y becomes 1 minus cosine squared y. And 1 minus sine squared y, this one, now becomes what? Cosine squared y equals 1 minus sine squared y. Here, we have already derived it here, ito the Pythagorean identity. So we can now substitute. 1 minus cosine squared y is simply sine squared y. So we have sine squared y plus sine squared y because of this all over 1 minus sine squared y is cosine squared y. So we have cosine squared y plus cosine squared y, and then we have dy. So these two terms are actually can be added. Okay, so sine squared y, that becomes 2 sine squared y all over the same with the denominator 2 cosine squared y dy. Okay? But you know, these twos will cancel. Okay. And of course, we are left with sine squared y, cosine squared y dy. And now, using the reciprocal identities, take note that sine theta all over cosine theta equals tangent theta. So, since they are raised into squared, then definitely sine squared theta all over cosine squared theta equals tangent squared theta. So that's an identity again. So what are we going to do is, again, we are going to, let me continue here. We are going to use that identity. It becomes tangent squared y dy. So now, again, this is not readily integrable. Okay? So you have to find another way such that you can integrate this. But there is an identity that 1 plus tangent squared y equals secant squared y. Okay, so we have tangent squared y. So we isolate tangent squared y. We have secant squared y minus 1. So if we are going to substitute that, that becomes secant squared y. Okay, that would be equal to the integral of secant squared y minus 1 dy. And this is readily integrable. Okay? Using the properties of integral, we can separate it. So, integral of secant squared y is simply tangent of y. Integral of dy is simply y. And there you have it. There you have the answer. So, yeah. So, basically, we have used many techniques or identities here in order for us to arrive to the correct answer. Okay? So, yeah. So, for number 89, second to the last, we have the integral of tangent of w dw all over, we have 1 minus tangent squared w. Okay? So the very first thing we're going to do here is to actually use an identity on this and also use an identity on this, because we cannot actually direct integrate this, no? So we have sine w all over cosine w. So we know that tangent is sine w all over sine. So we also know that tangent squared w, okay, from what we have learned a while ago, that is equal to the tangent squared w, sine squared. So it becomes sine squared w all over cosine squared w dw. So yeah. So if we're going to simplify the denominator first, So I am going to cross multiply this. So that would be cosine squared W minus sine squared W all over cosine of W, copying the same denominator. So why did we use identity on this? Because it would cancel, the cosine would cancel the denominator here. Okay? So actually, that is the very purpose of doing that. So, no, of course, this is in terms of squared. Okay? So you've canceled one cosine there. So we have sine W all over. We have cosine squared W minus sine squared W all over cosine W. So this is an improper fraction. Okay? I mean, a complex fraction. So what are we going to do? When we simplify that, that would be sine omega, sine W multiplied by the reciprocal of the denominator. Okay, so sine W multiplied by cosine W all over cosine squared W sine squared W. Upon simplifying, that's how we simplify. Okay, so that this becomes sine W cosine W all over cosine squared W minus sine squared W. Okay, so that's how we uh, we actually do this, no? So take note also that there is an identity of sine 2x. Okay, so sine 2x equals 2 sine x cosine of x. Okay, and it can be applied also with W as the variable. So 2 sine W cosine W. But the problem here in the numerator is that we don't have any 2. So we can actually put 2 here, but we are going to offset the reciprocal of it. Okay, we're going to multiply it on 1/2. So that technically we are still multiplying it by 1. 2 all over 2. Okay, so we added a 2 there, but to compensate for that 2, we added also 1/2 outside of the integral sign. So technically multiplying the numerator and the denominator by 2. Okay, so now we have 1/2 integral of 2 sine omega, 2 sine W cosine W would be simply sine 2W. And using the properties or the identities again for this, cosine squared W minus sine squared W, cosine squared W minus sine squared W would actually be equal to cosine 2W. Okay, so now we have cosine 2W dW. Okay, so now we can use substitution. So if I let you as the cosine 2W, then the derivative of u would be negative sine 2W multiplied by 2 dW. So that would becomes negative 2 sine 2W dW. And I only have sine 2W dW on my numerator. Okay? So that is my uh, that is what I want to separate. Sine 2W dW. Okay, so if that happens, we can now perform the u substitution. So sine 2W dW is du all over negative 2 all over the u. So I can factor out negative 1/2. So this becomes negative 1/4 because 1/2 times negative 1/2 negative 1/4. So du all over u. So technically, this is negative 1/4 ln of the absolute value of u plus c. Take note, we have to go back to the original variable. So we have negative 1/4 ln of the absolute value of u, which is cosine 2W plus c. So this would be the answer in this given integral. Down to our last number, it's actually number 90. We have the integral of cosine beta. Then we have 1 minus cosine 2 beta cube d beta. So the very first thing that we are going to do here is that we should realize that cosine 2 beta has an identity. Okay, so we cannot actually integrate this easily without simplifying. So cosine 2 beta is a double angle formula, and actually it's equal to cosine squared beta minus sine squared beta. So if we're going to substitute that, so cosine of beta, we have 1 minus cosine 2 beta So that is cosine squared beta minus sine squared beta raised to 3 d beta. So if I'm going to distribute the negative sign, so this becomes 1 minus cosine squared beta plus sine squared beta raised to 3. Don't forget that is raised to 3 because of the given is raised to 3. All right. So what are we going to do after that? So as you can notice, we also have 1 minus cosine squared beta here. So sine squared beta plus cosine squared beta equals 1. So if I'm going to transpose 1 minus cosine squared beta or cosine squared beta, so this term is actually what? Sine squared beta only. Using the Pythagorean identity. So that becomes cosine beta. And then we have sine squared beta plus sine squared beta raised to 3 d beta. Okay, we can add this too because um, it's really the same. Okay, so it's just like we're adding x plus x, right? So this becomes 2 sine squared beta. Okay, if we add d beta. Now we try to cube that. We try to cube. So this becomes 2 cube is 8 sine squared beta cube would be sine raised to 6. We multiply if we are raising. We multiply the exponent. Okay? So d beta. So now it's easier. I can factor out 8 outside of the integral. You have cosine of beta sine raised to 6 of beta d beta. So it's easier now to integrate. Okay? You can let u of the sine by u substitution. Let u sine beta. Then du would be what? Cosine beta d beta. So yeah, we have 8 integral of our u. Our u is sine raised to 6. So remember that sine raised to 6, sine raised to 6 beta also equal to sine beta raised to 6. Okay? So we have u raised to 6. So that is our sine raised to 6 beta. Then cosine beta d beta, that is simply our du. So it's power rule. So we have 8. Then we have u raised to 7 all over 7 plus c. So we have 8 all over 7. Our u is sine beta. So we have sine beta raised to 7 plus c. So going back to the original u. Okay? So or also it can be expressed as 8 all over 7 sine raised to 7 beta plus c. So any of the two is acceptable. Oops. Any of the two is acceptable. Alright guys, so thank you so much for listening. Again, I hope you learned something. If you're new to my channel, please do subscribe, no, for more videos. So this is integration of trigonometric integrals, part 13, using trigonometric identities. So thank you so much guys, and God bless.